Now I'm going to get into multiple linear regression. I know we covered a lot of that last week, but I think this is a hard thing. It's hard to understand. I wanted to go over it in detail both times. This, luckily, is very similar. So this is the same concept as simple linear regression, except we have more than one predictor value. So that's what it's going to mean in this case. So we have a response variable just like we did before, but we have multiple predictors. So you can think of this as looking at the effect of multiple variables on that response variable at one time. So say we're looking, and I'm going to come in and show an example. Pull this down. So the first model we're going to look at, that's multiple regression. We're going to be looking at heart disease mortality again. And we're going to look at the percentage of high school graduation or higher and the percent married in this case. So we're looking at two factors and how they are associated with this mortality rate. So that is an example of multiple regression, and I'm going to run it soon. So that's what we can think of as multiple. So you would have two or more of these predictors in this case. It's going to do a similar thing, but you can think of it, what this means in practice. So when we have a coefficient for this percent of high school graduation variable, it will give us the coefficient. And what that means is the effect of the education while holding the percent married constant. So the coefficient is looking at basically the independent or the effect of that variable alone when controlling or accounting for everything else in the model, is how you can think of it. So you've heard the thing controlling for X variable. That's what that means in practice. We're pretending percent married is constant, and then we're finding that relationship between the education and the mortality rate. So that's one way of thinking of it. And here, exactly what I just said. Interpret the coefficient as the average effect on Y of a 1 unit increase in the predictor while holding other predictors constant. So this is a mathematical. You would explain this to somebody, and you can see why this is a weight here. So if we're going up, in this case, let's go here. So if the percent high school graduation or higher, it increases 1%, because we're looking at percentage points here. The coefficient is going to mean, so it increases by one unit or 1%. The coefficient tells us the average effect, or how much it will increase when we increase that value by 1 unit or 1%. Come in here, I'm going to show just real quick. We saw this one earlier. I am going to output our summary. So MLR, multiple linear regression 2. So we're going to go over this and more, but what that means in practice, as the percent of high school graduation goes up by 1%, then our response variable, heart disease mortality, goes up by 1.8%, or 1.8 units, sorry. So that heart disease mortality goes up by 1.8, basically a 1.8, as the percent of high school graduation or higher goes up by 1%. So I was looking for that earlier in the class, and because I wanted to explain that. That makes it a little more intuitive. That's why in data science, the linear regression is so heavily used, because that, when you don't get in any of the modeling stuff, that makes sense. It quantifies, basically, you can think of it as weight. You actually can, and you can explain what that means in practice to someone and they get it. That's why you always default to the simplest model, because it's usually the easiest one to explain, and it prevents overfitting, which that is important here. So I actually didn't put this in the slides, but this is something we're going to come back to over and over again. Say I had, in this case in my data set, I have 17 variables. So some of them are identifying what the counties are. So I have about, I'd say 14 response variables that predictor variables that I could potentially use in my model. Why is that a really bad idea to put 14 things in a linear regression model? The reason that's a really bad idea, so when we're looking at our predicted and our actual values, usually in practice, we're actually using this to calculate predictions. So when we use too many parameters or control variables, it is going to really, your predictions will not generalize to new data, or it will be so specifically tailored to your training data or the model that you're training, the data you're training the model on, that when you drop in new data, it's going to be ineffective. The predictions are not going to be accurate. That, if you don't totally understand that, we'll come back to that again and again in more detail. Okay. Any questions about that before we move on? Feel free to put questions on Slack because I'm totally aware. That's why I make this like a cap at 2 hours. I'm going to stop at 12:30. This is a lot to take in, and then you kind of have to go back. One thing that I do recommend, and that I've done, and pretty much anytime I learn something new, in the statistics sense, programming is a little different. I do something like you're doing today, get a high-level overview from someone. Then I find either videos online, Khan Academy. I have not used it myself, but people say that's a great place to go every time. I don't do well with verbally getting information, so I tend to not go for the videos because it doesn't sink in. So what I've usually done is get two or three textbooks, read the most general one, and okay, that sort of makes sense to me. Then I would go to a harder textbook. Okay, then I added a little more information. I understand it a little better, and then I would go on to maybe the third one. Okay, now I get the details. If what one person misses, usually someone else. Then after reading multiple descriptions of it, you'll understand it a lot better. So I do recommend something like that. It doesn't have to be a book. It can be videos. It can be Coursera. It can be anything. And that way you're getting multiple perspectives on this. And then usually the book will cover things that I don't cover, or I don't have time to cover, or I don't explain as well as other concepts. So I recommend doing that. So I told you that the R squared, we don't usually use that in practice. We usually use the adjusted R squared. This comes back to overfitting, what I just explained to you. So the more predictors we add, the more tailored our predictors are going to be to our training data. So we don't want to have too many. The adjusted R squared, when we look at R squared, it's always going to increase by different degrees, but it's always going to increase as we add more predictors. It's the correlation always going to increase. It's the way it is, the predicted versus the actuals. So in that case, we could the R squared would keep getting better no matter how many predictors we added, even if those predictors weren't really adding any value. So it's still going to look like it's getting better. The adjusted R squared deals with that. So it basically penalizes you for having a lot of predictors, and it penalizes that R squared value so that that we're taking into account how many predictors we have, and it helps you prevent overfitting. So if you're having 3 predictors that have literally no effect on our value, it's going to penalize you for those. Whereas if you have 3 predictors that really do explain a lot of the variation, it's actually going to look higher, a lot higher when we do penalize for. It's basically trying to take out the effect of things that are not helpful. And here, I'm not in detail, but you think of it as penalizing for the number of predictors. So, and this, there's one more assumption that now that we're using 2 variables, this comes into play because it doesn't apply when you have 1. So basically another thing for linear regression, and this is actually for machine learning and anything, If your predictors are highly correlated or they vary in similar degrees to one another in the same direction, so highly correlated with one another, then it biases our model. They have to be independent of one another. You'll remember that I went over that. So you have to, one of the assumptions is that your coefficients have to be independent. The interaction variable, which is at the end of my slides, is the one caveat to that. But our predictors have to be independent. If they're too correlated with one another, our model is no longer valid. Okay. So I am going to go over one more thing before then I'm going to show a full example. So how do you assess multicollinearity? This has to do with our R-squared. So the formula is very simple. 1 over 1 minus the R-squared value. That's called the variance inflation factor. Most of the time it's just called VIF. So over here, there are cutoffs for this one, actually. So that's really helpful. If it's around 1 or 2, there's really no multicollinearity happening there. If it's 4, you're getting to the point that's like a yellow. Like look into it more and see if we are actually having multicollinearity. If it's above 10, we got a problem. So that means our model is very biased. The more predictors you add, usually the higher these numbers get. And there's going to be a great example of that soon. So I'm going to go in and show examples of that. So hold questions if there's any until then.